So this is AP Chem FRQ number 1. There's a link to the Google site where all these problems are. So it's just a big document. It's got, I think I'm up to about 9 or 10 FRQs, and there'll be more posted. I'm going to try and hit the more mathematical topics as I go. So eventually I'll get a lot more equilibrium, kinetics, and electrochem. Most of the beginning ones are more on bonding and thermodynamics. So question number 1 is a kind of a hodgepodge of questions. And kind of the point of this is for you to get a chance to practice, but also to kind of get a sense of what the grading scheme is for the AP Chem. Okay? So I want to talk about what things that you're going to see that you want to provide certain answers for. So little ticks that they have when they're going through the grade. Okay? So this one is a problem about sodium chlorate. The beginning question says, write out the balanced reaction for the decomposition in the presence of manganese dioxide catalyst. Okay? So here we have sodium chlorate. And if you've never gotten the chance to see sodium chlorate decompose, it's quite phenomenal if you add in a little bit of any kind of organic material. So if you check my links on YouTube, I actually have where I put a gummy bear into molten potassium chlorate, and the Redox reaction is quite spectacular. You want to know that chlorates will decompose to form some type of gas. So when you're dealing with decomposition, you want to look at your polyatomic ion and think, what gas do I recognize that's part of that? For this one, you want to think oxygen gas. Okay? There's no chlorine oxygen gas. It's very common. Carbonates turn into CO2, other things like that. Now, it says in there there's a manganese dioxide. You don't need to include that. Okay? But if you do, you don't want to put it into the reaction. You would want to put it over the arrow to show that it's a catalyst. Okay? So sodium chlorate will decompose to form oxygen gas and sodium chlorate. Okay? And to balance, I would do 2 of these, 3 of those, and 2 of those. Okay? So that's a typical question you would normally have seen on question 4 on your FRQs for how to do a balanced reaction. Now you're going to see that embedded into questions. So likely part A's of a lot of the questions I expect are going to be write out the reaction for this. Okay, part 2 says, if you had this in a test tube, what would you expect to happen to the mass as time goes on of the test tube? So the answer to that is that the mass would decrease as time goes on. And one thing you want to highlight when you write this answer is that you want to say that the mass will go down in the test tube, but you also want to specify that that's because something is leaving it, not because the actual mass of the reaction is going down. Okay, so a common misconception is that gases don't have mass or that gases aren't things. And so they want you to be very clear that you say the mass decreases, but then you want to follow that up and say that that's due to the oxygen gas leaving. Okay? So that's it for question A. Question B then starts to get into solubility in water, and so part B says draw the Lewis structure. Now, what's tough about this is that the Lewis structure of chlorate is going to involve resonance. So when you're drawing the Lewis structures, you want to put the single atom in the middle generally. Okay? So then you're going to have oxygens all around. Now, people get better and better at Lewis structures when you start to accrue formal charge and oxidation numbers and schemes for doing these exceptions to the octet. This one, I would start by simply saying, well, there has to be a bond between those 3 things. Okay? And then from there, I would start to think, okay, what's the total charge of this ion? How can I connect this in a way that makes sense? Since I have a -1 charge total, I'm going to do it where I have 1 oxygen that has a formal charge of -1. So this single bonded oxygen has an extra electron from what it began with. In terms of formal charge, it has 7 around it, and so it has a -1 charge. Now if I look then, this has 0, this has 0, this has -1. I need this charge to also be 0 so that the total formal charge is my total charge. Currently I have 1, 2, 3, 4, 5 bonds to that chlorine, which gives it 5 electrons for my formal charge. So putting another pair of electrons on it takes care of everything. That would be my Lewis structure for the chlorate. And then what I would want to do next is I would want to redraw that where I shift the double bonds and single bonds. Okay, so I'm going to have the chlorine with a single bond here, and a double bond here, and a double bond here. And I would do 1 more where the single bond is here, and then really I would enclose the whole thing in brackets and say, okay, that whole thing is my Lewis structure. It's the combination of those. Now, for those of you who are at a higher level, when you're going to take organic chemistry, you're going to need to know what's going on with these electrons. So if you watch, what's happening is 2 of the electrons from this oxygen are coming in to form this double bond. So when you see this double bond here, it's not like the bonds are actually changing places. Rather, the electrons are moving within this structure. These 2 electrons come here and form this double bond. So you'll see that there's a lack of electrons here and a double bond is formed. And then as that happens, that's going to force out these electrons here so that chlorine's electronic structure stays within something that makes sense for it, okay? Something that's stable for it. And these electrons will pop out. So if you look, these electrons have come from here, these electrons have come from here, okay? So, and then likewise, we could do that again to show how it would go back, and we could look at how it formed the 3rd resonance structure, okay? And then really, these electrons are all delocalized, and what you'll see is that the combination of all 3 of these little structures is what the actual molecule looks like, okay? So then part 2 says, you know, what makes this then soluble in water? Okay. So this is probably something that you wouldn't see on an AP test, but I like the question. The big idea here is that there are 2 things. One, that you have charge. So you actually have a negative charge on this chloride ion, and that negative charge is going to be very attracted to the hydrogen ends of the water molecule. So if I draw a water molecule here sideways, this portion of it, this end of that water molecule, has a lot of positive charge, so it'll be very attracted to that negative charge. Okay. Beyond that, the chlorate ion is very polar. Okay. Oxygen and chlorine. So oxygen and chlorine, I really shouldn't say very polar, but oxygen has electronegativity of 3.5, chlorine of 3. So there is a difference enough there that you're going to get electrons being withdrawn in all directions from the chlorine, which is going to leave a positive region. Now because of this lone pair, that shape is going to be trigonal pyramidal. So this is something that can have an asymmetry that will allow it to be a polar molecule. This end, and I've drawn this very poorly for looking at shapes of this. So I've got my electron dots there, but this end right here is going to be where the chlorine atom sits in a plane above the 3 oxygens. And that end's going to be positive, which is going to allow it to attract to the oxygen of the water molecules. The 3 oxygens, not only do they have that negative charge, but they also have extra electron density being drawn in towards them. And so that's going to have a negative charge on the bottom, and that's going to allow the hydrogens to attract. So between those 2 factors, you have a lot of charge density that's allowed to interact with the water molecule. Okay? Now, I would say that putting down that there's charge, putting down that it's polar is good, but really you want to highlight how that will interact with the water molecule and show that you understand what's happening when these things dissolve. That the water molecules are surrounding this, and that the different parts of the water are interacting with different parts of this. Okay? Good. All right, so then from there, it takes a twist into thermodynamics. Okay, so I'm going to spin our camera a little bit. So now we're going back to this reaction of part A, and now we're going to analyze the thermodynamics of it. So sodium chloride decomposing. So it says what's delta H, what's delta S, what's delta G. Okay? And what you should know about sodium chloride decomposing and a lot of decomposition reactions is you have to provide energy to get it to happen. So the enthalpy for that is going to be positive. Now, when you learn enthalpy, usually it's poorly taught because it's a very difficult concept. If you look at the definitions of it, they're very technical and they don't make much sense. What you want to think of enthalpy is you want to think of it as an energy content of the chemicals. And we specify what we mean by that. So for example, one of the really confusing things about enthalpy is if you look at something dissolving and the water cools down, we say that delta H is positive. But if I heat up water, then the delta H for the... I'm sorry, I'm saying that poorly. Let me repeat that one more time. If I do a chemical reaction in water, in aqueous solution, and the water's temperature goes up, we would say that delta H for that is negative. But if I just heat up water and I get it to boil, we would say that the delta H for that is positive. And the subtle distinction in those 2 cases is that it's what are you looking at? Are you looking at the water or are you looking at the chemical process? Okay, so for this, I would be looking at the chemical process. So even though I would have fire involved and all kinds of energy, for the most part, I'm putting in more energy than I'm getting back for this reaction. So from perspective of the chemical, of the sodium chloride decomposing, the enthalpy of that is a positive change. The chemical itself is gaining energy from the surroundings in order for this reaction to occur. Okay? So I would say that the enthalpy change for that is positive. It's endothermic. And the energy is put into the chemical. Or the chemical process. Okay? Second part says, what would the delta S be? So delta S, you want to look immediately for gases. So if I go back to my reaction, I had a solid sodium chloride turning into oxygen gas and solid sodium chloride. So delta S is definitely going to be positive for this. And the explanation, again, entropy is something that's not well understood for most high school students. We teach it to you as disorder. That's not what it actually is. That just gives you a correct answer. But for the AP test, you can explain entropy in terms of disorder, and they will not mark down. Okay? So for this, I would say you have more gas molecules as products than as reactants. That's your key line. And then from there, you could additionally state that that's an increase in disorder, which links back to your entropy. You could also go through and say that it's an increase in microstates, it's an increase in dispersal of energy, and that would be the perfect link back to entropy. Okay. So the last question then says, well, will this reaction be spontaneous or not? And if so, when? Okay. So that's hinting at Gibbs free energy. Now again, a lot of these things are constructs. These are things that humans have come up with for a purpose. Gibbs free energy does not have a definition. It's not a thing. Okay? It's something that we have constructed that says, will a reaction happen or not? And it combines enthalpy and entropy changes. Okay? So we're looking at energy, which again is a very mathematical shortcut kind of thing for physics. So for Gibbs free energy, really, you're not going to understand what it is. You're only going to understand its purpose. And that's hard for you to come by as a high school student. If delta G is negative, that tells you the reaction is spontaneous. It'll happen without you having to do anything as long as those chemicals or whatever is in contact. If it's positive, you can have those things in contact and it's not going to happen. Okay? So for this, the question is, will this be positive or negative? And what you want to do then is you want to analyze the Gibbs free energy equation. Okay, this is a common thing to come up on the AP test. So it's equal to your enthalpy change minus the temperature times delta S. Your temperature is in Kelvin, so it'll always be positive. So if I look at the signs of this, I have a positive value for delta H, which is going to make delta G be positive. I also have a positive value for delta S, and since I'm subtracting that, that's going to make delta G be negative. So those two things will battle. So the question really is, when will this be spontaneous? When will this be negative? Okay. Well, it's going to be spontaneous when this delta S is multiplied by a greater factor. So this will be spontaneous at high temperatures. Okay. At high temperatures, I'm multiplying a large number times a very large, or times a positive value. So I'm going to subtract a greater and greater quantity to get a more and more negative delta G. At low temperatures, this might not compete as much with the delta H, and therefore delta H is going to dominate, and that's going to be non-spontaneous. Okay. Now if we go back, that makes a lot of sense. What we were doing is we were heating up sodium chloride to get it to decompose. Ergo, if it's at a high enough temperature, it'll decompose. If it's not at high enough temperature, nothing will happen. Okay? So that's the bulk of the problem. The very last question then asks for a redox reaction where you're mixing a chlorate with something. Okay? And redox reactions are very difficult. Reactions are difficult, and these are of the most difficult of all the types. So a couple tips for redox reactions. One, it's hard for a lot of kids to figure out how to know they have a redox reaction. Okay, so you want to start to recognize chemicals that have lots of oxygen in them, things like permanganate, dichromate. So in this case, we're taking potassium chlorate, and we're going to react that with sodium nitrate. Now you'll notice when I'm writing this down that I'm omitting the potassium and the sodium. Okay, and that's because I know those are going to be spectators. There's nothing insoluble that can form with either one. So I don't want them in there. I just want to do the reaction with the parts that I know that are going to be relevant. And that's a great tip for redox. It will really help. Okay, the second thing is you need to know what these turn into, which is a memorization thing. And a lot of these chemicals are not as typical for a high school class. So that's hard. So chlorate is part of a sequence. Chlorate, hypochlorite, chlorine, or chloride. And this can turn into any of them. You can pick whatever you like. I would recommend you pick something simple. So for this one, I would pick chloride or chlorine because they don't have any oxygen. And that's going to make this easier to balance. Okay? So let's go ahead and pick chlorine. The nitrate. Okay. This one has not come up very often. You actually have a couple options, I believe. I believe you can turn this into NO2 or NO3 minus. I'm going to turn it into the nitrate. Okay. So these aren't things that you can predict per se. These redox things are more so based on memorization. Then from there, you need to take the two things that go together and put them into half reactions. So I'm going to take things with chlorine, turning into chlorine gas. Okay? And then what I'm going to do is I'm going to balance that reaction. The other thing that's tricky about redox is that you don't just have the things in the original reaction. You're doing this in solution, and usually it's acidic or basic. So that means that you have water available to balance. And you also have either H pluses or OH minus. In this one, we're doing acidic conditions. So when I go to balance this, I'm going to start and just quite simply say there's 2 chlorines here, there's 1 here. So I need 2 chlorines. And then I have 6 oxygens, and I don't have any oxygen here to balance. So a lot of people get stuck at that point. What you want to do then is just start adding water molecules. 6 waters. Okay? Now I have 12 hydrogens. I need some hydrogen over here. So I'm going to add 12 H pluses. Okay, and then the last part, it's tricky for kids as well. You have to balance the charge. So I have 12 positive charges, 2 negative charges, no charge, no charge. So I have 10 extra positive charges over here, more so than the other side. So I'm also going to add 10 electrons to the side. Okay. Then I'm going to do the same process, but with the second reaction. I'm going to take this nitrate and nitrate. Okay. And I'm going to do the same thing. The nitrogens are balanced. I'm going to add a water. And then I'm going to go ahead and I'm going to add 2 H pluses. Okay? Minus sign, 2 positive signs. So I need 2 electrons here. Okay? Now, what I'm now going to do is I'm going to recombine both of these half reactions. I'm going to combine the reduction one and the oxidation one. And then I'm going to end up with a final reaction that's balanced in every element. So every single element will be balanced and every single charge will be balanced. Okay? In order for that to work, the number of electrons need to cancel. Okay, so that's going to help balance my charge part of this. If I just combine those 2 reactions, all of my numbers of things will add up. But the charges will not. So to do that, I need to have 10 electrons here. So the second reaction, everything in it is going to get multiplied by 5. And that'll give me 10 electrons, and it'll give me more of everything else. So when I'm done, I'm going to have 12 H pluses plus 2 chlorates plus 5 water plus 5 NO2 minus is all my reactants. Then, all of those are going to combine, and I'm going to make chlorine gas, 6 waters. I'm going to make 5 nitrates. I'm going to make 10 H pluses. Now, even after all that work, even though I have a balanced reaction here, you'll notice that I still have a little bit more stuff to do. Namely, I have to start canceling things out. So I have 5 waters, 6 waters. I'm going to cancel 5 of them to leave me with 1. Okay? Then I have 12 H pluses. I'm going to get rid of the 1 here, leaving me with 2. Cancel out these 10. Okay. So that would be it. So this would be 2 H pluses plus 2 chlorates makes 5 nitrates, chlorine gas, a water, 5 nitrates. And if you look, everything on that will balance. Okay? I have 2 positive charges, 2 negative charges, and 5 minus charges. So there's a total of 5 minus. And if you look at this side, I have no charge, 5 minus. So not only my nitrogens, my oxygens, my hydrogens, my chlorines all balanced, but in addition to that, all of my charge is balanced. Now, if you're at the higher end level of AP Chem, and you understand most things, and you're at the end of the year, then you'll know that also that nitrite is a weak, is a byproduct of a weak acid. So in acidic conditions, really I would have to go through and add an H plus to each of these, which would end up giving me HNO2s instead of NO2 minuses. Because if I have nitrite in a solution with lots of H pluses, that's going to form that bond between the two. So a weak acid is going to have a strong bond with H pluses. So really I would probably have to add These two H pluses here, 3 more to this part, and then that would mean I would need 3 more H pluses on the other side. But that's it. That's your balanced redox reaction. So I'm going to zoom in on that so you can see that nicely in case you haven't yet. And that's FRQ number 1. So if that's helpful, please check out the rest, and I'll try and get a whole bunch up.